Hi, welcome to Errors and Uncertainties. Let's say we measure the mass of the electron, which we'll call ME. The result we get from our measurement will not be exactly the same as the true mass of the electron. This is because measurements are not infinitely precise. The difference between the measured value and the true value is called the error. So in this case, the error is ME measured minus ME true. Now, the term error does not indicate that a mistake has been made or say that a measuring device has malfunctioned. It merely reflects the fact that measurements in practice are not perfectly precise. Let's look at a few examples of sources of error in measurements. Let's say we want to measure the length of this pencil with this ruler. Sources of error in this measurement include the following. The ruler has gradations that are only so small. It is difficult to measure much more precisely than the size of the smallest gradation. Also, just how carefully can we align the ruler and the pencil? And also, we can think of a few more exotic sources of error. For example, the ruler length will change slightly with temperature. How much has the current temperature affected the result? How precisely was the ruler made to start with? And, for that matter, the pencil length will change with humidity, temperature, etc. Is the length of the pencil under current conditions even the quantity we actually want to measure? Maybe we want to know it under very specific conditions that are different than what is happening now. How much will this change the result? Okay, next example. Let's say you have a business that sells some product that you ship to customers, and you want to estimate how many shipments will be returned per year. So, you decide to see how many are returned over a given 30-day period. Then, you plan to scale up this result to get an answer for a full year. To make this example simple, let's say that your business operates under pretty much the same conditions year-round. Your product sells at a near constant rate, and you use the same manufacturing and shipping methods all year. Even under these conditions, the number of returns in each 30-day period will not be the same. They are subject to lots of tiny random acts of chance. For example, a given package may get damaged in shipping, or a certain customer may be particularly dissatisfied with the product for very individual reasons. So, your measurement of the rate of returns will be subject to these fluctuations. The error introduced by these fluctuations is called statistical error. Okay, now let's look at the role of measurement error in science. In science, we, roughly speaking, use the following procedure. We have some phenomenon that we observe in nature that we wish to explain. So we make a hypothesis to explain the phenomenon, and then we test that hypothesis using experiment and observation. If the experiment or observation does not agree with the hypothesis, we discard the hypothesis. However, if it agrees, we keep the hypothesis around for future tests. Now, this step of testing the hypothesis via experiment and/or observation often means making a measurement of some kind. To illustrate, imagine a particle physicist comes up with some great new idea. It solves some problem in particle physics. This model has the side effect of predicting the lifetime of a certain particle. We can go and measure that particle's lifetime to see if it agrees with the value that the model predicts. But how do we test the model's prediction if the result we get from the measurement isn't equal to the true value? Don't worry, not all is lost. We can compare the measured value to the prediction if we can get a value for the typical size of the difference between the measured and true values. In other words, we need a value for how large the error will typically be. This quantity is called the uncertainty. For a given measurement, we pretty much by definition do not know the error. We have the measured value. If we knew the error, that would mean we knew the true value, which we definitely don't know. One of the common ways of expressing a measurement and its uncertainty is through Gaussian error bars. We'll go into what Gaussian errors are and the conditions under which they arise later on. But for now, let's just see how a measurement and its Gaussian error bar are quoted. Let's say a new particle is discovered and its mass m is measured. The experiment quotes a result with a Gaussian error bar that reads m equals 757 plus or minus 43 GeV over c squared. Here, 757 GeV over c squared is the central value, and 43 GeV over c squared is the uncertainty, often denoted as sigma. When we plot the measurement with its Gaussian error bar, the central value is in the middle, and the error bar extends from the center in each direction by the amount sigma. Now, the uncertainty is a value for the typical expected size of the error. The error in any given measurement may be bigger or smaller than the uncertainty, and it may be positive or negative in sign. This means in particular that the true value of the quantity we're measuring is not guaranteed to be within the plus or minus 1 sigma error bar. Okay, now let's ask, but how do we get the uncertainty? In practice, this is often not easy. It requires a really good understanding of one's measurement apparatus and techniques. All the important sources of error need to be taken into account and evaluated. Sometimes estimating the uncertainty is the most difficult part of the measurement. Okay, let's get back to the big picture about how we test scientific hypotheses. We measure quantities to test against the predictions of our ideas. We've seen that the measured value will have an uncertainty, but there's yet another wrinkle. The predictions of our hypotheses have errors and uncertainties too. Why do predictions have uncertainties? Let's look at two reasons. First, scientific models usually take measured quantities, which have error bars, as inputs. And second, scientific models also have simplifications to make them tractable and practically useful. First, let's look at uncertainties from measured parameters. Let's go back to that example of a particle physics model that predicts a certain particle's lifetime. That prediction depends on parameters, such as the mass of the particle and the masses of the particles it decays to. We don't know those masses infinitely precisely. They are measured quantities, and that means they have uncertainties. These uncertainties feed into the prediction for the particle lifetime. This means that we cannot predict the lifetime with infinite precision. Our prediction will have an associated uncertainty. So, uncertainties in measurements mean that model parameters are not infinitely well known, and this leads to uncertainties in the model predictions. Okay, now let's look at uncertainties from model simplifications. Let's say we're modeling the movement of a planet around its star. We can measure the planet's distance to the star, its velocity relative to the star's mass, etc. We want to figure out where the planet will be at a certain time in the future. We can use the laws of physics to make this prediction. But there are other bodies in the universe, and those other bodies will exert gravitational and other forces on the planet and star. We can't ever include all of these effects in our prediction. These effects will introduce errors into our predictions. We can try to identify the largest of these effects and estimate them to get an uncertainty on our prediction of the planet's position. But there will always be effects which we do not include. These simplifications will lead to uncertainties on the model's prediction. Okay, let's briefly summarize what we've seen. The take-home message here is the following. Neither measurements nor scientific predictions are infinitely precise. Both have sources of error. But through careful studies, we can estimate the typical sizes of these errors. Through those studies, we can then assign an uncertainty to our measurements and predictions. These uncertainties have a critical role in determining if we reject or keep a given scientific hypothesis.